Good morning, lovely 12s. Right, buddies, today is the lesson that you have all been so excited about. Today is our big mathematical induction revision lesson. How exciting! So, the goal for today is I just want to refresh your brains a little bit on what proof by induction is, even though you probably don't need too much of a refresher. I'm just going to do one question with you because I think that'll be enough to get you fresh and ready to go, and then I'm going to give you the vast majority of the time to do as many proof by induction questions as you can, because that's how you get good at them, is by practice, 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 practice. Cool beans. Okay. Yeah, so I think this topic's really cool, and let's just jump right in. Cool. The one question I'm going to get you to do is actually from the worksheet that I'm going to be setting you in a sec. It's question 4, and I just thought it was a bit wonky, and so I thought this would be a good one to do with you. That way you'll be able to know how all the wonky ones work, you lucky ducks. Okay, so here we go. It says, prove that the sum of the first n terms in a series, and it lists it out like that, including these ones. So it lists it out like that, and you want to prove that all of that lot is equal to the to what's given down there. So you want to show that it's equal to this. Okay? So that's the proof that we're asked to do. Now, first of all, this isn't super important, but it might be if you go off to university to take maths or something that's linked to maths. Why is proof by induction a good idea in this case? Why would I want to use induction, apart from the title saying it's the big induction revision day? Well, yeah, that's right. If you want to use induction, my buddies, it's a good one to use for series, because it's a good one for when you're counting on, okay? When you're dealing with kind of distinct cases, and then it goes from one to the next, which is exactly what a sequence is. Proof by induction works really, really well for those. It's the same as like when we did those matrix questions and you raised it to a power. Well, if you're raising it to a whole number power, you can see what it is for squared, then cubed, then 4, then 5, and so on and so on and so on. Things like that are what induction's best for. Okay. Now, again, here's why I picked this question. I think it's quite awkward, this, because look, it says 1 times 3 plus 2 times 4 plus 3 times 5, and it's meant to equal that. So that would be our conjecture, right? That's our hypothesis. That's our conjecture is what we call that in maths. So, yeah, like, it's essentially, it's saying this, it's saying that 1 times 3 plus 2 times 4 plus everything else for up to whatever is going to equal n plus 1, 2n plus 7, all over 6. Right. There's a mega problem with this, I think. And the thing is, the left-hand side is certainly very awkward. Okay? The left-hand side's awkward, awkward, awkward. Because, like, what's the target expression going to be if you're to think ahead? Because it's only just got numbers and no letters. So how in the devil are we supposed to get a target expression? Well, what should we do first? I don't like the left-hand side written as it is. Well, if you said rewrite it so it's in summation notation, that's exactly right. So if we use kind of the series notation, you're going to be onto a winner with that. So rather than writing it like this, which hasn't got algebra, which is a real problem, and we also don't know what the last term is, so even this plot dot plus dot 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 is even rubbish. Like, well, I guess it did specify it's the first n terms, but this has got an end point as well. It is plus something else. So, I don't know, it's not ideal. So here's what we're going to do. Let's rewrite it using series notation. So here we go, summation notation. Well, to start with, it's the first n term, so we got to get up to n. We're going to start at 1, but we need to actually use a variable to do that. So we can't be using n, because we're using that to be the last term. We could use k, but we usually use k in our proof, so we won't use k. So let's use r, because you usually use r when you're doing sequences anyway. Now, you just have to come up with the pattern. If you look just in the first term, this one's a 1, this one's a 3. This one's a 2, this one's a 4. The first term has a 1 there. The second term has a 2 there. The third term has a 3 there. What will the nth term have? What will the rth term have? Well, an r. What is that getting times by? Well, 2 more than the r. This is your sum. This is your sum. Do you guys see that? Yeah? Because it's whatever term you're on times by 2 more than the term that you're on. And that seems to be the pattern. So our conjecture, buddies, is actually this. This is what we're going to prove. 1, 2n plus 7 all over 6. Now that's the conjecture. That's what we're going to prove. Okay. Now then, my buddies, now we can do our actual proof by induction. I'm going to be cheeky and cut and paste. Of course, I can't do it straight away. I'm cutting and pasting this onto the next slide because I reckon I can do this in one page. So here we go. That's what we're going to try to prove, okay? That is what we are going to try to prove. Okay, so here we go then, buddies. Step one. So essentially, right now, you should already know what to do. So I'm going to say, just get ahead of me. Go. And if you want to follow along, here we go. Step one every time is to do the base case, right? And the base case is for when n equals 1. So you start with the first term, just because n equals 1 is the easiest. You don't have to start at n equals 1, but it would be very unusual not to. So here we go. Let's go on the left-hand side. Well, on the left side here, you're going to be having this. You're going to be going, well, it's going to be the sum of r equals 1, but only going to 1, of r plus 2. Well, you're only putting 1 into it, so this is going to be 1 bracket 1 plus 2, which is going to be 3. Happy days? What's the right-hand side equal? RHS. Oh, I forgot the H in that. I've done it my Canadian way. Okay, RHS. On the right-hand side, what do we get? We'll pop 1 in and see. 1 times 1 plus 1 times 2 lots of 1 plus 7 all over 6. And here's what we've got. We've got 2 and 7 is 9. 9 times 2 is 18, times 1 is 18, divided by 6 is 3. So it confirms. We've established a base case. Next one, my buddies, is what do we do next? You remember? That's it. You assume. Assume. True. For n equals k. Okay? If you assume it's true for n equals k, that's the crux of these. That's the reason that proof by induction works. And if that was true, that would mean this. That would mean that what we've got on the left-hand side here is that the sum of all r equals 1 all the way to k, not n, is just going to be this. It's going to be r plus 2. So that part didn't actually change, my buddies, because it was still r. Yeah, we're swapping n out for k, not r out for k. And then on the right-hand side, what it would equal is it would be k plus 1, 2k plus 7. So there you go, all over 6. So essentially got that just by looking at this majestic guy up there, okay? So that's what that one is. That's beautiful. That's what we're going to look at. Now, again, most important thing of all is that assumption. That's going to be key to us solving the whole thing. So hope you're okay. We swapped n's out for k, but not r's, just n's out for k. Cool. Now what's the next step, buddies? That's it, the target case. Okay, the target expression is for when n equals k plus 1. Now, what will it look like then, buddies? Well, on the left, it's going to be almost the same. It's going to be, let's go back to black. It's going to be this on the left-hand side. It's going to be r equals 1, but this time we're going to k plus 1. But this doesn't change in here, though. This is still r plus 2. Yeah, because we're just changing what we're counting on to. We're not actually changing the rule. Now, this side, though, changes. If it was k plus 1, if our assumption were true or whatever, if this is true, then on the right-hand side, it would be like this. It would be k plus 1. Then this would be k plus 1 plus 1. 2k plus 1 plus 7. So if our assumption is true, this is what the target would have to be. All over 6, which simplifies down to this. It simplifies to k plus 1, k plus 2, and 2k plus, 2 times 1 is 2 plus 7 is 9, 2k plus 9, all over 6, okay? Now that, again, that's super important also. That's our target expression. So when we do our proof, if we can get to that, then that means that we've actually done the proof by induction step, which is awesome. Okay, what's our next step again? That's it. You prove from the left-hand side. So you prove from the left-hand side. Cool? Well, you prove from the left-hand side, and you do that also for n equals, well, you prove from the left-hand side for when n equals k plus 1 also. Cool? So what have we got on the left-hand side? Well, it's here. It's the left-hand side of the target expression. You've got this. You've got the sum of all r equals 1 all the way through to k plus 1, because it is the next case up, of r and then r plus 2. Now, here's where you got to be clever. we're going to do k plus 1. Well, essentially, my lovelies, if you want to do one more than the actual base 1, here's what you're going to get. This is going to be the same as r equals 1 all the way through to k of r plus 2, plus 2, plus the next one along, okay? So that brings you up to k, and then you just have to also do then the k plus 1, which is going to be, k plus 1. So let's do it. R is going to be k plus 1, and k plus 1 plus 2. K plus 1 plus 2. Do you see that, buddies? I hope, because if you went for trying to go from 1 all the way to k plus 1, we can instead just go from 1 all the way to k, and then add the k plus 1 in, and that's what we've done. But oh my gosh, do you see anything cool? Oh great, the bell is going off, how exciting. Now you really feel like you're in school. It's important that we have a bell, you know, when there's like 10 people in the school. I think it's really important we keep the bell, so yeah, good times. It's not important, that's sarcasm. Okay, so here we go. Anyway, we can then swap out, look, this thing here from 1 to k of this r stuff actually subs out for our assumption. That's what we assume to be true. So here we go, that is k plus 1, 2k plus 7, and then underneath we got over 6, and then on this one here we're going to get plus, and this is just going to be k plus 1, and I'm going to simplify this one to k plus 3. Important, my buddies, that we include something in this, and those are these words here, from assumption, okay? Because we don't necessarily know assumption. So, assumption. What am I even writing? I'm going to rewrite that because I can't even tell why I've spelled it wrong. Assumption. A-S-S-U-M-P-T-I-O-N. That's not what I wrote the first time, but I couldn't figure out what I wrote the first time. So there you go. From assumption. Yeah, absolutely. Because we don't know that's true. We've just used our conjecture there. So we're trying to prove it's true. Okay. So what are we going to do next then, buddies? Like, what are we going to do? Because we have to get to that target expression. Well, there's no addition in the target expression. So let's figure out a way. Let's do a common denominator and see, shall we? Yeah, let's do that. Okay, so if you're going to do a common denominator, here's what it would be. It would be k plus 1, 2k plus 7, then you're going to be all over 6, and then this would be plus 6, k plus 1, k plus 3, all over 6, which means that then they can go together. Well, certainly the denominator is 6, which is good, because that's what we're going for. And then on the top, what are we going to get? Well, I think a k plus 1 is common. A k plus 2 isn't, so I'm not quite sure yet what's going on. So let's just have a try. I see k plus 1 is common, and I don't see anything else, so I'm just going to try for now and see what happens. I'm going to factorize the k plus 1 out of the top two. So I'll be left with k plus 1. Then I'll be left with, missing from the first is a k, open bracket 2k plus 7. That's what's missing from the first one. Now from the second one, what's missing is the 6 and the k plus 3. Okay, so now I'm in a muddle, but it's alright. I think we can still do it. So here's the deal. I'm in a muddle now, so I'm better than I was though, because there's no addition in it anymore. Everything's trapped in a bracket, but I'm not sure. So what are we going to do? Times out. Let's see if we can tidy it. Potentially that's the way forward. I think it is actually. So 2k squared plus 7k plus 6k plus 18 is what you'd get in that bracket. Still all over 6. Here we go. Then we're going to get k plus 1. Here we're going to get 2k squared plus 13k plus 18, and I'm just hoping to myself, please let it factorize is what I'm thinking, all over 6. Now we got to try to factorize. That bracket is a quadratic, so potentially it factorizes. Looking for two numbers, that times to make 2 times 18, which is 36, and they have to add to make 13, so times to make 36, add to make 13. It could be 4 and 9, which it isn't. It could, which it is actually. Yeah, 4 and 9 are the two numbers. Yeah, 4 and 9 are the two numbers that do that. Yep, I think. So here we go. So it's going to factorize to this, my buddies. It's going to be here, I'm going to show full steps. Okay, 2k squared plus 4k plus 9k plus 18 is going to lead to brackets. It's going to be 2k, k plus 2. This next part here is going to be plus 9k plus 2, which then of course leads to, I'm going to run out of space, oh dear, oh yeah, come on, don't flip the page yet, don't flick the page. Yes, okay, which means that the top, my buddies, factorizes to this. It factorizes to the k plus 1, which is chillin', so k plus 1, which is just chillin'. They're long, aren't they, my buddies? K plus 1. And then here we're going to be left with k plus 2 and the 2k plus 9 from our factorization. All over 6, which then you look to the left and you say, oh, thank God, it's the target expression. So we've actually hit our target expression, haven't we, my buddies? So that's it. You've done the actual proofy bit now. So it's just now to the final steps, which is your statement. Now, do you remember what the statement is? I hope so. Well, your statement's this then, buddies. So this is the target. Okay, target. So we've got to our target. Here's your statement. If the result is true for n equals k because that's what our red is, okay? That's what we just assumed that that's true. If it's true for n equals k, then it's true for n equals k plus 1. Okay, so if it's true for n equals k, you've shown it's true for n equals k plus 1. But since it's true for n equals 1, that means it's true for all positive integers. It's true for n equals 2 and all positive integers. All positive integers. Do you get that, buddies? I hope. Perfect. And then final thing is just your concluding statement. Thus, and here it is, our original equation, which is up there in blue, the sum of 1 to n of r plus 2, thus the sum of r equals 1 to n of r, what was it again, r plus 2? Yeah, it was r plus 2 is equal to n plus 1, 2n plus 7, all over 6 by mathematical induction. Whew! By mathematical induction. Cool. Now, I would say that was a tricky one. Definitely. That's definitely the answer. I've written down my thing correctly. And n plus 1, 2n plus 7 all over 6. Yep, brilliant. So, yeah, that's good. That's an example of a hard one. I hope that you paused and got ahead of me and you just didn't follow along with me, but you actually got ahead. And here's what I'm going to get you to do for the rest of the lesson. Okay. I've attached this sheet for you to work on. So it's level 2. It's harder, okay, from the Integral website. And I want you to do the best that you possibly can to do a mix and to get as many done as you can, okay? Just to really drive home that you understand the steps and what you're actually doing when you do a proof by induction, okay? I just did 4 because I thought 4 looked like it was a bit wonky. 5 looks wonky to me as well. And then these guys underneath actually look easier to me. So what I would say is do a mix of what's left. So maybe pick one of that, maybe do 5 and 6, and then maybe a couple of these guys too, or 1 or 2 of those as well. So just make sure that you try various types of functions, sequences that are defined explicitly like this, or sorry, series that are defined explicitly like this, series that you have to come up with a rule for, like question 4, things that aren't series, so powers like question 6, implicit or recursive series like question 7, matrices like question 9 and 10. Just do a mix of everything, okay, buddies? I want you just to make sure you've tried all sorts of different types. And when you're all done, take a picture, pop it online, and that's the end of me, my buddies. So good luck, and see you next time. Bye, buddies!